Okay, so with those notes out of the way, I'd like to thank everyone again for joining us in today's webinar, Climate Change Impact Analysis using HydroGeoSphere. As climate change continues to shape our world, it's becoming harder and harder to rely on historical patterns of precipitation and temperature as part of hydrologic studies. And this is why HydroGeoSphere is an incredibly powerful tool for long-term climate change impact analyses of hydrologic systems. As a physics-based simulation platform with a de-emphasis on the use of empirical relationships, HydroGeoSphere is an exceptionally powerful tool for modeling unknowns. These unknowns can include regions with little or no observation data, but more importantly, this physics-based approach is the most realistic and reliable way to simulate how water resources systems will react to future climate conditions. In this webinar, Dr. Andre Erler will introduce key topics and considerations that should form the basis for all climate change impact analyses using HydroGeoSphere. Andre is the senior climate scientist here at Aquanty. His main expertise lies in regional climate modeling and applications to hydrology and hydroclimatic extremes. Andre joined Aquanty in 2016 in order to study the impact of climate change on water resources and agriculture in Canada, and to provide insights into climate change impacts to end users. Andre, thank you in advance for making yourself available for today's webinar. Take it away.
Hey, thank you. I hope you can all hear me well. So, okay, yeah, we have a lot of ground to cover today. There are essentially 4 sections to this, and the first one would be general introduction to climate projection, IPCC climate models, and that sort of stuff. Then I have a section about HydroGeosphere and the boundary conditions that you specifically have to consider, and so some pitfalls that you have to take care not to fall into. Then there's a section about data preparation, and that also includes downscaling, bias correction, some data sources. And then we'll close with a case study where I'll walk you through climate change impact analysis that we've done. And then you'll have the opportunity to sort of ask questions and maybe also sort of interrogate our choices there. Each of these will probably take about 15 minutes, so we'll be here for a while. Hope you all have your coffee or beverage of choice. And so after each section, I'll briefly pause and look at the chat if there are any questions. So if you have questions, put them in the chat. Afterwards, we'll also have some time for discussion, right? Okay, so climate projections in general. We now are at the 6th iteration of the IPCC assessment reports. In fact, the census report was actually just released yesterday. The physical science report was already released in 2021, and then impact and mitigation last year. I do not necessarily recommend to read those reports because they're extremely long and very technical, but there are summaries for policymakers. All of those have summaries, and then there's a synthesis summary as well, which this is what I would recommend to read first. One thing that is important, if you already have experience with the 5th assessment report and some climate change impact assessment that was done in that context, the greenhouse gas scenarios have changed, but mainly in name. So now they're called shared socioeconomic pathways, so SSPs. They used to be called RCP, so representative concentration pathways. But in most cases, equivalent scenarios still exist, and I'll highlight that. Now, the 6th assessment report is based on CMIP 6. CMIP 6 is actually separate as an entity. It's so the IPCC does not run its own climate projections. It relies on projections that are published by CMIP. CMIP is the Coupled Model Intercomparison Project, and it's actually the 5th iteration, but to keep consistent with the IPCC assessment reports, they call it CMIP 6. There are also regional assessments, and it used to be the case that in CMIP 5 and the AR5, these were published in the assessment reports as well. This is not the case anymore. They talk a bit about regional impacts, but they rely now more on national scale assessments and also Cordex, which we'll talk about later as well. On the right-hand side, you see the temperature projections for the different scenarios. So as I said, they're based on the CMIP6 coupled model intercomparison project. This is sort of just a very high-level summary of the results. So on the left-hand side is temperature, and on the right-hand side is precipitation. The temperature increase that's projected here based on different scenarios. So we're looking at temperature increases. So these are normalized to relative to like the most recent period. We're looking at something in the higher scenarios at 4 degrees, whereas in the mitigation scenarios, we're looking at like 1 degree, right? Very aggressive mitigation. Whereas for precipitation, this is actually a lot more uncertain. You can see that the spread is also much larger. So these bands indicate the spread between different models. We're looking at precipitation changes on the global average that vary between, let's say, 3 and 5%. So in the global average, that's not that much. However, you see the maps here. These are projected changes, and they're scaled to the increase in temperature. So to an approximation, they actually apply to all of the scenarios. And these are just to indicate the patterns. So for temperature, one thing that is very pronounced is Arctic amplification. So much higher warming in the Arctic. So in Canada, for example, we are now almost at 3 degrees warming. And on land areas in Canada or in the Arctic, you'd expect about a threefold increase in temperature compared to the global average. And this is to a large extent because of snow feedback. Whereas for precipitation, the picture is much more complex. So in the tropics, the green is an increase in temperature, and brown is an increase in precipitation, and brown is a decrease in precipitation, so drier. There is a projected increase in the tropics, but also at very high latitudes. In mid-latitudes, and this is annual average, in mid-latitudes, there's generally an increase in precipitation. A decrease is really only in subtropical regions, so in Australia, Central America, Mediterranean. However, there are also seasonal differences. I'll get to that too. And in mid-latitudes, the seasonal differences are such that in winter, there's generally a higher increase in precipitation, whereas in summer, there are many regions in the subtropic that will experience a decrease, and even outside of the subtropics. So this is just a very high level, right? So for Canada, North America, mostly on average, in the annual average, an increase in precipitation. This is not necessarily true in every season though, so keep that in mind. CMIP is a very complex project. It has many different sub-experiments. And that's sort of illustrated in this circle bullseye figure. There's really only the scenario map and the historical simulations that are of interest for a climate change impact analysis. So most of these experiments are really for scientific purpose primarily, and sort of sensitivity testing and model development, right? So you can actually ignore most of those. So scenario map is the one that you would probably be interested in. The socioeconomic pathways or shared socioeconomic pathways, there's this grid here. They have different scenarios from sustainability to fossil fuel development. And then these are paired with different sort of radiative forcing changes or mitigation scenarios. And generally, the SSP1 is sort of the stronger mitigation, and then fossil fuel is, of course, no mitigation, and these are the higher impacts. So there's sort of a diagonal that goes through that here. You can convert RCP scenarios to SSP scenarios basically by just looking at the last 2 digits. So RCP used to have these 8.5, for example, or 6.0. And these are still appended after the dash to the SSP scenarios as well. And the meaning of these 2 last digits is the same. So an SSP 5-8.5 is essentially the same scenario as RCP 8.5, although I think it actually turns out to be a little bit more aggressive, but yeah. A scenario that is now often recommended for impact analysis if you cannot afford to run multiple scenarios is the SSP 3-7. So that's sort of, it's not the worst case scenario, but it's a relatively high impact scenario. Now, briefly about climate models. So I'm assuming a lot of you guys are probably hydrologists or have a background in hydrology. So you're familiar with modeling, but not necessarily with climate modeling. And there are important differences between climate models and hydrological models, generally speaking, although actually HydroGeoSphere is relatively similar to a climate model in the sense that climate models are essentially CFD models, so computational fluid dynamics. They solve the momentum and mass conservation equations. So essentially a version of the Navier-Stokes equations on a rotating sphere. They also include thermodynamics, density, buoyancy. That's why we need density, of course, right? They also do that in the ocean. So they're coupled between atmosphere and ocean, and then they have sea ice components. They have a land surface model as well, which handles things, for example, like snow, but also vegetation processes, and to an extent, a simple version of land surface hydrology as well. Typically, these are column models, so this is an important limitation. So the land surface is a column model. The atmosphere is full 3D. The ocean is full 3D as well. So it resolves the full circulation. Subgrid scale processes are parameterized, however, and it's not mentioned on the slide, I realize, but the resolution of a climate model is typically about 100 kilometers, so fairly coarse. Grid cells are very large. Cloud formation processes, for example, are not resolved. Those are parameterized, solar radiation as well. But essentially, at the large scale, they're PDE solvers. They're based on fluid dynamics and thermodynamics. So now let's talk about a very important topic, and that is uncertainty and the sources of uncertainty. And this is something that there's some differences to hydrology again. And so on the right-hand side, the figure is a plot of the temperature anomalies over the historical period that's simulated by different climate models. And this looks very messy, and that's kind of the point. There is the red line, that is the multi-model ensemble mean from CMIP 6. And then there's the black line, or it's multiple black lines, and these are observational estimates of the surface temperature anomaly globally averaged. Right? And you can see that the multi-model ensemble mean actually cuts through the observational estimates really well. The observational estimates, interestingly, have higher variability, so they have all these jiggles around, right? And there's a reason for this, and this is natural variability. I'll talk a lot more about that. This is individual models have that variability too, but in the multi-model ensemble mean, it's averaged out, right? All the color shading, these are the ranges of different models, right? So the calibration period, if you want to call it that way, sort of in the 20th century, it's fairly tight there. If you go back to 1850, where there's a lot of uncertainty about the boundary conditions as well, the model spread actually gets quite large. And then the more you go into the future as well, right? But the ensemble of models has quite a bit of spread, and there's a lot of variability. And each individual model integration has a lot of interannual variability that's sort of represented here in the observations as well. And so, as I said, the models have that too, right? So what sources of uncertainty are there? There's this internal variability, that's natural variability. That's essentially these jiggles that you see in the observations as well. And the climate models have that too. And I'll talk actually quite a bit more about that. There are two other major forms of uncertainty, and that's scenario uncertainty. So that's related to these SSP scenarios. And then there's model error. And this on the right-hand side is a figure of sort of the relative contribution of uncertainty to the these different sources of uncertainty to the overall uncertainty at different lead times. So we start out 0, that's about 2000, and then 100, that's 2100. So the further we project into the future, and this is from a fairly old study, but it's pretty much still the same. The largest source of uncertainty at the end of the century is scenario uncertainty. And this is just, do we have a mitigation scenario or no mitigation scenario, right? That really controls the outcomes at the end of the century. And this is an uncertainty that we as modelers cannot really address. That's a economic or political question. And that's just something we'll have to live with. We'll have to explore different scenarios. Model error as a relative contribution is relatively significant if you're looking at the current climate or near-term predictions. But it dwarfs at the end of the century compared to the impact of the change in boundary conditions from the scenario, right? It's also important to note that actually the model error doesn't get smaller in the future. It remains the same. It's just that the relative contribution gets smaller, right? And another one is internal variability, and this is this natural variability, these jiggles that you've seen, right? And over short term, this is very significant. So for weather prediction, this is essentially dominates weather prediction. But then it becomes really small if you average over a long time period or over a large area. However, if you look at a smaller area, so this is just averaging over the British Isles, which would be for a regional climate model, a typical scale, right? Then the main point here is that internal variability increases by several factors. And so if you're looking at a small area, and if you're looking at a small watershed that's smaller than the British Isles, this becomes even worse. Natural variability, and this can be things like El Nino, but also just weather. And I'll talk a little bit more about this in a minute. This becomes a really significant factor. So, and this is essentially just noise from the climate system. It exists, it's natural. So it's not a model error. But it really makes the analysis very difficult, and you need a lot of statistics, and you need to be very careful about how you interpret your analysis, right? So keep this in mind. The smaller the area, the higher natural variability. Now, what is the source of this natural variability? A lot of this is related to things like ENSO. So ENSO is El Nino Southern Oscillation Index. So it's essentially El Nino and La Nina, the cycle. It has a period of about 2 to 7 years, but it's not a fixed period, right? So it varies. And this is the ENSO index. So basically, if it's red, we have El Nino, and if it's blue, we have La Nina. So you may be familiar with this. And so it does look like it's somewhat periodic, but it's pretty messy, right? And this is a coupled ocean-atmosphere mode, so it arises from the interaction between the ocean and the atmosphere, and just has this quasi-periodic behavior. And this is a lot of what drives internal variability. So this long timescale interaction between the atmosphere and the ocean. And this is not forced externally. It's something that's generated completely internally, right? Even if you wouldn't change the forcing, greenhouse gases or whatever, this would still always happen in the climate system. There are more of those. So ENSO is one of those, and this is or El Nino, and this is sort of the footprint in sea surface temperature that El Nino has, and it's actually really large. So it really dominates the interannual variability in the Pacific and even globally. Then there's another one, it's called PDO, that's relatively relevant for especially the Pacific Northwest. That has a somewhat longer time period. So you may have heard of it, Pacific Decadal Oscillation. So it's about 15 years. These are the power spectra. So usually you can do a power spectrum, and if the power spectrum is not just a peak, but it's fairly broad, that's usually sort of like one of these chaotic behaviors, right? The PDO actually has 2, and ENSO has 2 as well. And just to hammer this home a bit more, natural variability and ensembles. So this is a study that was really interesting. It was done with a large ensemble of the same climate model. So it's about 10 years old now, but so they used an older climate model so they could run a really large ensemble. And they ran 30 members of that ensemble. So 30 different integrations, all the same model, same parameters, same scenario. Just slight perturbations to lead the natural variability into different directions. And the average in precipitation change is shown here. So similar to what I've shown before. So increase in the north and in the subtropics, or in the south and Central America, towards Central America, decrease in precipitation. But then if you compare the wettest member of that ensemble and the driest member of that ensemble, and I think these are 30-year periods averaged at the end of the century, right? The wettest member of this 30-member ensemble actually shows an increase in precipitation even in the subtropics, whereas the driest member shows extreme drying, right? But these are equally valid scenarios. They are unlikely, but they are both results of the same model integration that yields this average result. And so if you're just looking at a single ensemble member, you have to be prepared that you're unlucky and you're getting one of these end members. And this is why you need to basically use an ensemble approach. Similarly, if you're just looking at a single grid point, the projections, so this is just for Seattle, Washington, right? This is the precipitation anomaly, and so 25 to 50%, right? Over the historical period, so this is what it looks like historically, right? Quite a lot of variability year to year. But then there's some ensemble members again that show an increase and some that show a decrease. So it's pretty inconclusive for this single point. If you average over North America, typically your results get more consistent and you get an increase. This is not always the case. So in this case, if you're just looking at the southern part of North America, it's less consistent. But then if you do a global average for these models, it's really consistent and the noise is really small. So it really depends on the size of the area that you're looking at and the time period, how long the time period is, how large the effect of natural variability is, right? So keep this in mind. If you're looking at a small watershed, this is a big problem, okay? So the way to think about climate change then in this sense is more statistically. And so we can start with weather prediction. So when you're trying to do a weather prediction from an initial condition, weather prediction is an initial condition problem, right? You can basically think of the climate as the statistics of the current weather, and that's sort of illustrated by this lightly shaded envelope, right? So that's the possible distribution of weather at your location. That's the and in your season, and that's the climate, so what we would call climate, right? And then if you have a particular set of initial conditions that you're forecasting from, then that constrains the possible outcomes and you narrow this distribution, but it's still a distribution. So there's still a randomness in this prediction. And you're running an ensemble, and these are all these different squiggly lines that are shown here. You're running this ensemble to probe the shape of this distribution that is now most likely, and that is a subset of the climatological distribution, right? So this is a way to think about this. And so with climate change then, the way to think about it is that climate change is a shift in this distribution of potential weather events, right? And this can be a shift in the mean of that distribution, but it can also be a shift in, or a change in the shape of that distribution. And so what we're doing with an ensemble of climate models is that we are probing this distribution and to experimentally derive the shape of the distribution. Another way of doing this is averaging over a long time period. So if you have a single model and you're averaging or you're taking statistics over, let's say, a 30-year period, then you're sampling actually a lot more of that climate distribution. The problem is, of course, that between different models, this distribution has a somewhat different shape. And so by sampling over a large multi-model ensemble, we are actually sampling a larger, sort of more representative distribution. Right, and so the differences in model bias, that's basically shown with the green distribution, that each particular model may actually have a subset or a different, slightly different distribution compared to the actual climatological distribution. Right. So this is just sort of the conceptual framework that I would encourage to think about climate. It's the statistics of weather, and it's a change in the distribution of weather. Right. Okay. So this concludes basically this section here. If there are any questions, we could briefly answer them now. The main takeaways are climate models are essentially sophisticated physical models. The greenhouse gas scenarios essentially determine the outcomes. So this is the biggest uncertainty. There's a new set of those scenarios too. But for our purpose, the main confounding factor when we are dealing with impact assessment is really the internal variability. A corollary to that is climate models do not follow the historical trajectory of weather. This is often a misunderstanding. So when you're looking at the output from a climate model over the historical period and you compare this to the historical record of weather. It will be somewhere in the same ballpark and the distribution will be similar. But the actual trajectory, if you plot annual and like year to year, the temperature or precipitation, it will look different. There will be dry periods when there historically have been wet periods and vice versa. Don't expect it to match. And this is by design. Climate models do not reproduce the weather because they're not initialized in that way. Yeah, and they're inherently probabilistic. There's actually now a question. So Abdu asks, the projected precipitation changes in CMIP 6 are related to rainfall quantity. Are there any projections about rainfall variability? And do individual climate models capture the variability better than ensemble models? Yeah, so climate models do essentially predict variability, because so they actually have internally very short time steps. So the time step of a climate model is something like 15 minutes or half an hour maybe. So they do produce day-to-day variability and even hour-to-hour variability. The problem is that they're coarse resolution, so about 100 kilometers. So they do not represent weather systems that are smaller than that very well. So small-scale convection is poorly represented in climate models. So the statistics of small-scale convection are probably not right. And the variability day-to-day or year-to-year may also not be right. Year-to-year variability may be better. So a lot of climate models actually reproduce something like El Nino. So they have reasonable year-to-year variability, but it's still somewhat different than the actual observed ones. If you take an ensemble mean, especially multi-model ensemble mean or even ensemble mean over a time period, so let's say you average each year, that actually smooths out most of the variability. So if you're interested in variability, you have to draw that from an individual model realization and not from an ensemble mean. Yeah, so thanks for that question. So now to HydroGeoSphere. I'm assuming a lot of you probably are aware of HydroGeoSphere, but if you're not, I'll just briefly, HydroGeoSphere is a surface-subsurface integrated hydrological model. So essentially, it solves the fluid dynamics of the 2D surface and the 3D subsurface. It solves the full 3D Richardson equation in the subsurface, unsaturated as well. Surface water and groundwater are fully coupled. There's also a channel domain. So this is essentially surface flow in a 1D channel, and there's a channel network then, and that fully interacts also with this, the 2D surface and the subsurface. Land surface processes are relatively simple, and typically you would couple with a different land surface representations, and I'll get more into that now that I talk about the boundary conditions. This is just a brief sample of sort of what an HydroGeoSphere simulation can look like. This is at a very small scale, essentially spilling from pothole to pothole, and then infiltration in the subsurface, right? And at the bottom, you can see the groundwater table. And so you can see a perched water table forming, and then through fractures, there's infiltration through that. And you can run a HydroGeoSphere at a much larger scale too, but you can also run it at this very small scale. This is actually true for a lot of climate models too. You can run them at much higher resolution in principle, but it's just computationally very expensive. Yeah. So boundary conditions. So HydroGeoSphere is essentially a deterministic PDE model, right? So it solves the Richards equation. That means it is primarily determined by boundary conditions and also initial conditions to an extent if you're running a time-dependent simulation. But boundary conditions are really important for HydroGeoSphere. And there are essentially two types of boundary conditions. There are lateral boundary conditions, which are mainly hydrological. So the surface water flow, so you may have a stream that flows into your domain or flows out of your domain. And then there may also be an aquifer that's connected to your watershed, and that would be a lateral head boundary condition, right? And so these can be really problematic. There are, but also top boundary conditions. These are essentially the climate boundary conditions, and climate change is essentially about the change in these top boundary conditions, right? So there's liquid water influx at the top. So that's precipitation primarily, but also snow melt. But then there's also evapotranspiration. So we have to prescribe potential evapotranspiration, and then there are vegetation processes that will result in actual evapotranspiration. So first, the lateral boundary conditions. So the best way to go about this is to have no flow boundary conditions, right? So if you can construct your domain in a way that you have no flow boundary conditions, you're basically good. You don't need to worry too much about this. And I encourage you to do that. If you have stream inflow or even an aquifer that's connected to your domain, this can be a very big problem because your watershed does not change in isolation. In a climate change scenario, the hydrology in the surrounding regions will change. So the heads in the boundary, the constant head boundary condition to the aquifer will change because the heads in this aquifer will change because of a change in the large scale hydrology, right? And you need to account for this in some way, and this can be very difficult. You may be able to draw on published studies or on a large scale model that somebody else or you yourself have run, and then you could run a nested model and you can draw boundary conditions from that. That's a possible approach, but otherwise it's very difficult. And if you don't change the head boundary conditions accordingly, it can really affect your results, right? Imagine if your head boundary conditions really drop, you can input or lose a lot of water from your domain, right? So in practice, build bigger models. This is just an example here, the Athabasca River Basin. It's a really large model. We have a model for that. It's 160,000 square kilometers. At that scale, you're pretty safe, but you don't have to go that big. So usually a few thousand square kilometer watersheds, that's probably enough. I just want to mention we have this Canada Warm Water project that aims actually to develop data sets that help you build these large models. So it's possible to build large models, and they're typically better for boundary conditions. But now to the climate boundary conditions. So this is a very important aspect, of course. One aspect that I'll have to talk a lot about is snow. Precipitation is something you can essentially take with bias correction, and that's a caveat, from the climate model. But snow is something where you often have to do a little bit more work and where you have to do potentially some modeling, and then potential evapotranspiration. I'll also touch about this. It's important to know that climate models actually produce a lot more output than temperature and precipitation. They have the full energy and mass balance at the surface and even in the 3D atmosphere, but that's less interesting, right? So, yeah, with statistical bias, statistical downscaling and bias correction, there's another problem with this, but I'll get to that. So snow melt is more difficult because it happens at a very small scale, and you may have to model that yourself. If topography is not a major factor in your area of interest and you need snow, actually there's a tip I can give you. Most climate models, or all climate models, have energy balanced snow models, and they output snow melt and SWE. So you can actually use that if you don't want to do snow modeling yourself. If you do snow modeling, it's very important to take a physics-based energy balance approach. It's still very common in hydrology to use temperature index models, and I'll talk about that. And that's basically what we not recommend to do. Use an energy balance model. And energy balance here really means that it considers solar radiation and different sources of energy, doesn't parameterize everything based on temperature. Right? There are many options. HGS doesn't have an energy balance model included, so you'll have to run that offline. In-house, we run Snowball and NOAA. We are switching to CLM right now, but there are also very sophisticated models like Crocus or Alpine 3D that these models are used for avalanche forecasting. So they represent essentially every process that you can think of in snow, layering, 50 layers, everything you want. So you can get very complex on this, but it's often not necessary. So temperature index models, there is a big problem with those. they parameterize everything based on temperature. And so the picture on the right is just sort of the complexity of snow, right? So it's very small scale. And in a watershed, if you have some runoff or snow data, you can calibrate the temperature index model to reproduce snow melt relatively well. And that's mainly empirical, and you can get rid of a lot of the complexity. And so it's very tempting. They work well if they're calibrated for a historical period. But if the climate changes, they have to be recalibrated because the relationship between all these different processes changes, right? There have been studies that have shown that even over the historical period, the melt factors have actually become inaccurate if the model is not recalibrated to the new sort of climate regime that we already have, right? And the reason, so the root of the problem here is that you're parameterizing the incoming solar radiation with temperature. But temperature changes because of a change in greenhouse gases and not because of a change in solar irradiation. Solar radiation stays the same. And so if you have this, if you're implying this relationship, it's going to, basically your model is going to draw a wrong conclusion and will assume that solar radiation increases, right? As temperature increases, but that's not the case. So it just gets the physics wrong. So yeah, don't use temperature index models. This also has implications for PET. There's similar approaches for PET to approximate PET just based on temperature. And this is just some very simple calculation I've done for, I think it's some area in Alberta. I've taken data from the Canadian Regional Climate Model in this case, computed PET from it from 1950 to 2100, and this is the result. With different methods. So you can see that there's some that show a strong increase, like the red line here, right? This is a pure temperature index model. The yellow one too. That's a Thornthwaite method, by the way, quite popular. So it shows a strong increase over the 21st century. But if you compute it from the Penman-Monteith method, which is essentially the gold standard, and the climate models give you all of that output, you actually see a very small increase. It's only by 20%. And the reason is that temperature increases, yes, saturation deficit increases a bit, but solar radiation doesn't, right? And so the red line, and so the Priestley-Taylor method, that's the purple line, does take into account radiation explicitly. And so you actually see a very similar increase as with Penman-Monteith. The calibration level is a bit different. The red line and the yellow line, they parameterize solar radiation based on temperature. And the predictable result is that they predict a very strong increase in potential evapotranspiration, which is not physical. So they're projecting an increase of over 50%, right? This is unphysical. But if you use a temperature index model, this can happen. So be aware of that. Yeah, main takeaways here, don't use temperature index models. Gold standard for PET is Penman-Monteith. You can calculate Penman-Monteith from climate model output. At least use something like Priestley-Taylor. Consider snow and snow modeling. You may have to do snow modeling offline. If your hydrological model only has a temperature index model, I would recommend doing snow modeling offline with a physics-based model. Yeah, and so for lateral boundary conditions, best is to just have no flow if you can justify it. Okay. There are any questions? I don't see any in the chat, so I'll just move on. So data preparation, essentially just a few notes about bias correction and downscaling. To start you off, there are a lot of data repositories and data sources that you can use to get climate data. A lot of those, unfortunately, are just based on GCM, so global climate models, fairly coarse resolution. The Pacific Climate Impact Consortium has a suite of statistically downscaled GCM projections. They're only for Canada, they're only for temperature and precipitation. So that's a bit of a limitation. They have a fairly good range of CMIP6 and CMIP6 models. So this is a good data set, except that they don't have radiation and it's only Canada. So you do actually have to add some data here. There's also climatedata.ca. They have a lot of data, also historical data. It's really for non-technical users primarily. The climate projection data they have is usually reserved mainly from PCIC. But these are good resources to be aware of. For technical users, there's also, of course, the CMIP 6 model archive. There you can download all model output, everything you need. Radiation, humidity, the dew point, convective precipitation, precipitable water, sea ice, anything you want. But it's for fairly technical users. You will get netcdf files. It's a lot of data. And well, if you go into that, look at the scenario map. That's also important and historical. There's also Cordex. So Cordex is a regional climate model. It's essentially an index of data. It's not really a repository. There's also a lot more. This is just a small selection. Cordex is also more for expert users. So, and since I've mentioned it, Aquatics is the coordinated regional downscaling experiment. So it's essentially a coordinated effort to produce regional climate model projections. It's very focused on regional climate models, although technically it also includes statistical downscaling. There are chapters for all major regions on the globe. This is the domain for, or the suggested model domain for North America. And there's Europe, Africa, Asia. All major regions have Cordex chapters. Right? This is not limited to North America. Typically, the model resolution is about 0.44 or 0.22 degrees, so about 40 or 20 kilometers. And their suggested scenario, by the way, is SSP 3-7 for Cordex 2. But there are hardly, or I'm not aware of any models already being available for CMIP 6. So all of what Cordex currently have is downscaled from CMIP 5. So the climate projections are a bit more dated. So regional climate modeling, I've mentioned it a couple of times. What is it actually? It's essentially running a nested model in a global climate model. And this is usually done offline. So you run the global climate model first, then you take the boundary conditions, you apply these boundary conditions to a regional climate model that runs at much higher resolution. So typically something like 20 kilometers, right? Whereas the global model will be 100 kilometers or worse. And this is a good illustration of sort of the effective resolution of these models, right? So this globe, actually, it does show you what the resolution of the global climate model is, right? So the Mediterranean here is pretty blocky. And actually, the Strait of Gibraltar is not even represented, although they usually put it in artificially. Whereas in a regional climate model, actually, you can see most of this, like the Alps are there, all the major mountain chains, the British Isles, the Channel, everything is there, right? So this is why regional climate models are used. They have much better representation of the regional geography and also regional climate drivers of climate, like lakes, mountain ranges, and I'll get more into that. Statistical downscaling, very briefly. So you can apply to GCMs directly, but you can also apply to RCMs and then downscale to a very small scale. There's a lot of statistically downscaled data available for GCMs that downscales them to about 10 kilometer resolution. So in this sense, you're at a similar level as a regional climate model would get you. But then you can also drive that even further. Statistical downscaling essentially already includes bias correction. So you don't need to worry about that separately. But there are two main issues that you have to contend with. And the biggest one is the stationarity assumption. So you're essentially assuming, so the way statistical downscaling works is that you're deriving a relationship between a predictive relationship about how a variable output in a global climate model relates to a small scale value on the ground at a very high resolution. So essentially a statistical relationship, right? And you're assuming that this relationship remains the same in a future climate, even though the climate may change quite drastically. So your snow seasonality may change completely, right? but you're still assuming that the relationship between temperature at a large scale and a small scale will stay the same, even though maybe there are different elevations, for example, right? So this is a major limitation. Regional climate models aim to address that. Then if you don't have a large set of statistics here, the problem is also that if you only have a short calibration period or not a lot of data, you may be overfitting. So you may be fitting the climate model output to a climate period in the observational record that it was maybe not representative. And this introduces additional uncertainty. So be aware of that too. A little bit more here. So essentially it's a necessary evil. In practice, in hydrological modeling, you typically have to do some kind of downscaling or bias correction in order to get the water balance right. This is unfortunately just a fact. Also, if you're using a regional climate model, you will often not get the water balance right. You may have way too much snow. Your watershed may end up being snow dominated, even though it shouldn't be. So you may have to do something about that. My philosophy is, as much as necessary to get realistic behavior in your hydrological model, but as little as possible, as little as you can get away with. There are two popular methods, or so that are sort of the end of the spectrum of the methods that are used. The delta method is essentially you just take the anomalies or the change signal from the climate model and just apply it to your high resolution observations. This will always give you a perfect match to the historical record during the historical period. But especially when you're thinking about things like snow, if you can just add that or subtract that, that's questionable. And then for precipitation changes, you will not see any change in the variability. You're essentially assuming that the variability is constant. Quantile mapping is sort of the opposite end of the spectrum. You actually massaging the data a lot. It will give you a very good fit to the distribution, but it is prone to overfitting and to the inflation, so the inflation problem. And you can read the literature on this, but quantile mapping has an inflation problem where you can overestimate changes. So that's something to be aware of. Something else in this context, I personally like to use aggregated data and climate normals, especially for model spin-up. So on the right-hand side, you just see sort of a figure of climate normals for a watershed. So purple is PET, so it peaks in summer. Green is precip, and then snowmelt is yellow. So there's no snowmelt in summer, of course. And this is, I think, for the Grand River watershed in southern Canada. And so what I essentially do is I take a 30-year period. For each month, I average the climate for that month, and then run an average seasonal cycle with the hydrological model. And this is pretty good for spin-up. There are major problems with this, though. One thing is PET and also snowmelt are highly nonlinear. So computing that from averaged values is not recommended. So you should compute PET and snowmelt from daily or even sub-daily climate model output and then average it afterwards, or use the climate model output directly, which is what we did here. Another limitation is that you're losing intermittency. So you're distributing an average amount of precipitation over an entire month. You're not getting like days with high precipitation and then days with no precipitation. In arid climates, this is a problem. In wet climates, it's typically not a big problem. Okay. One thing I want to add also about this is, so I mentioned before, we have this Canada One Water project. We're doing regional climate modeling for this. So we're doing regional climate simulations, and we are also assembling a lot of data. And we have this really nice slide background here that I'm showing for the project. So you see the logo in the lower right. The aim of the project is to build really large-scale HydroGeoSphere models for all of Canada, and you can see the mosaic of models on the right-hand side here. We will also use the weather research and forecast model, WRF, to downscale dynamically the CMIP 6 climate projections. A lot of the data will be publicly accessible. We are also looking specifically at land surface processes like permafrost as well. For the regional climate modeling for C1 water or Canada 1 water, we'll be essentially following the Cortex 2 protocol. We'll use the SSP 3-7 scenario and ERA 5 for historical. We'll be running the simulations at up to 12.5 kilometer resolution, up to 2100. So this is coming up. They're not done yet, but you will be able to draw from that. And we'll be conditioning these data sets for hydrological modeling. So the main takeaways here are that there are a lot of repositories for climate projection data. Most of them are based on statistically downscaled GCM data, so global climate models. Unfortunately, a lot of them only have temperature and precipitation, most of them. And that's just because these are easy to downscale statistically because there's a lot of observational data available, right? For a physics-based approach, for snow as well as potential evapotranspiration, you also need radiation. And therefore, for that, you usually have to go directly to the model output, and that's a bit more technical. Same is true for regional climate models. Usually you have to go to the output directly, to the model output. When you're designing a study, and this is, we will talk more about this now, and this is the last section, really consider your regional drivers of the climate, and this will determine whether you can use a GCM or an RCM. It's something where you just have to understand your region and what is important, and this is a judgment call you'll have to make as a modeler. Bias correction is a necessary evil. You'll have to do it, probably. If you can get away without bias correction, that's great, but probably not. And then keep in mind this Canada 1 water project. There's a lot of data that's coming up that will be usable for climate change impact assessment, and that will really help you. It's not finished, so a lot of this is still in progress, but soon there will be a lot of data available. Yeah. So now we'll get to the case study design. I see there's one question about the difference between CMIP 5 and CMIP 6. Maybe we can table that for later because it's a very general question. And let me just go over the case study for now. And the case study is actually based on CMIP 5 because we did it about 5 years ago. Okay. So first, we used HydroGeoSphere for this. Why do we recommend to use HydroGeoSphere for, or something similar like an integrated hydrological model for climate change impact analysis? The main reason is, so if you're interested in groundwater, you have to assume that the surface water is going to change as the climate changes. So this means stream flow seasonality, but also recharge is going to change. So whatever you've estimated for recharge for the historical period is probably not valid anymore because precipitation and evapotranspiration will change. So you really need, if you're interested in climate change and impacts on groundwater, an integrated approach. But even if you're primarily interested in surface water, there's still an argument for an integrated approach, and that is if you think that base flow is important in your watershed. And I don't know how you're parameterizing base flow. If you're using a rainfall runoff model, there's some base flow parameterization in there. You'd have to think about how you adjust that in a changing climate. But in an integrated model, this is automatically dynamically handled, right? So you really think it makes the boundary conditions much easier to take an integrated approach. The case study we are using here is the Grand River watershed. So it's in southern Ontario, southern Canada, in the Great Lakes region, right? We were interested in climate change impacts on hydrology, but specifically also groundwater, because that's something that hasn't really been looked at before. But we also looked at stream flow and soil moisture, right? We used a model that was already calibrated and existed in-house, the Grand River model, which you see on the lower left-hand side. That's sort of like the layering. It has 17 layers, and it has about 33,000 nodes per sheet at a resolution that varies between about 250 meters to 1 kilometer. We also have higher resolution versions of that model, but because we had to run a lot of scenarios, we chose a lower resolution one. This study was published in Water Resources Research in 2 articles, so you can read up all the details there. However, there are a lot of limitations to that study, and maybe you can try to pay some attention and see where the weaknesses are, especially in the light of what I've told you before, what things you have to pay attention to, right? So maybe a little bit of active learning, and try to, afterwards we can criticize the study, okay? So first, the selection of the climate data. So we have to understand what's really important in our region. And in the region that we're looking at here, the Great Lakes are really the dominant drivers of climate. And in particular, the snow belts. That if you live here, you know what that is. So there are some regions, Waterloo is one of those, where sometimes when the wind is blowing in winter over the lakes, you will get a ton of snow. The Adirondacks, for example, in New York State are also some of these regions. Algonquin Park, if you've been there, very nice skiing conditions. So these are lake effect snow events or lake effect precipitation, more generally speaking. And so you really want a model that represents the lakes. And unfortunately, that's typically only regional climate models. Global climate models don't represent the lakes well. There's a group called GLISA, the Great Lakes Integrated Science and Assessment. They have a lot of resources on this. They did reviews on climate models and looked at how they're representing the lakes. So if you're living in the Great Lakes region, visit their website and look at their material. It's pretty good. We were also interested in seasonality. So this region has really hot, almost tropical summers, but snowy winters, and then of course spring freshet. And the question is, of course, is it still going to remain snow dominated, or is there maybe going to be a change, right? So snow is important too. The model we chose, and this is to an extent out of convenience, and this was actually pre-Cordex, so is a regional climate model ensemble from the University of Toronto. They've added a lake model to the weather research and forecasting model. So WRF, the Weather Research and Forecasting Model, is a pretty popular regional climate model in North America. It's from NCAR from the US. And so this they added a snow model, a lake model, and so this was basically the main point. It's also, we are collaborating with the University of Toronto because it's not far, right? This is the model domain. So there's an outer model domain that's 30-kilometer resolution. And then there's an inner model domain that's a 10-kilometer resolution. This is a common approach in regional climate modeling, this kind of nesting. And these resolutions are also pretty typical, 30 and 10-kilometer. Right? And there were 2 different configurations, and this will become important later. Right? There's the WRF-G configuration and the WRF-T configuration. So just keep in mind there are 2 different ones. Now, before you start doing hydrological analysis or hydrological modeling, you need to do some data analysis first and get a sense for how the models are behaving. And this is now for the historical period, we've looked at temperature biases. So these are deviations from the observed temperature. In the top row is summer and in the bottom row is winter. And I really recommend looking at seasons separately because biases can be very different in different seasons in climate models because they're governed by different processes, right? On the left-hand side is one of the WRF simulation ensembles. And on the right-hand side is the global climate model that was used to force or drive the regional climate model. And the main takeaway here is the biases between those are very different. And this is quite common. So the regional climate model has a cold bias, whereas the global climate model actually has a warm bias in this region, especially in summer. An exception is winter. So in winter, over the Great Lakes, there's a huge cold bias. And this is because the global climate model actually doesn't have a proper representation of the Great Lakes, and it just freezes everything here, right? So there's no open water anymore. There's no warming of the atmosphere from the lakes. It gets very cold. So this is a major limitation of most global climate models. Whereas for the regional climate model, there's a much more varied picture. It also has a cold bias, but that's more a general cold bias, not because of the lake. There is apparently a warm bias over the lakes, but this is actually an artifact of the observations because the observations are actually interpolated from the land. Actually, the surface temperature is pretty spot on. If you look at Boyo records, for example. So data analysis before you're doing hydrological modeling is important. One thing I can point out here is this is sort of the region, sort of here. I don't know if you can see my mouse. But this is the region where we are interested in. The biases in both cases are fairly homogeneous over that area, right? So we don't really need to do a grid point by grid point bias correction. But we do need to do a bias correction, right? Because this is clearly, it's too cold. The precipitation looks similar. So there's a positive bias here. So we need to do something about that. So this is average, the seasonal cycle, similar, like this is monthly normal seasonal cycle over the Grand River watershed. So similar to the figure I've shown before, the colors are the same. So green is precipitation. The dots are the observations, and the solid and dashed lines are the two different WRF ensembles. Especially one of them has a huge precipitation bias in summer, right? This is insane. Like, this is a precipitation bias, it's almost a factor of 2. And the other one has about 30% bias. And these numbers are not unusual. Climate models have biases that can be in that range. And this is summer. So in summer, most of the precipitation is convective, so it's parameterized. It's approximated in the climate models. It's not really resolved, and this is the reason why the biases are so large, or one of the reasons, right? So we need to apply a bias correction, and what we chose actually to do is a very non-invasive bias correction, where we just bias correct annual average, but liquid and solid precipitation separately over the entire watershed. And if we do that, we can reduce the biases. Now it's actually looking pretty good. There's still some bias. So in fall, our precipitation is too low. Snow is actually pretty spot on. So this is very good, very encouraging. And so this kind of bias correction now, this seems sufficient. We got reasonably good simulations with that. Yeah? Okay, so let's move on then. So the experimental setup. Here in this case, we did a time slice approach. So we did a historical period, a mid-century period, and an end-century period. Each of these periods is 15 years long. But for each of these periods, we have 4 ensemble members from WRF. So that means a total of 60 years per period. So this gives us pretty good statistics. And so this combination of a longer time period and multiple ensemble members, this is pretty common. The time period has to be chosen in a way that you don't have too much drift from climate change over that period. So 15 years is okay. 30 years is also okay, but kind of boundary. 100 years, obviously, you have a lot of drift, right? So you can't really do that. So drift because of warming, right? And so you have to supplement that with ensemble members. Overall, you want to have, if you're looking at sort of long-term averages, you want to have at least 30 years of combined data in your ensemble mean period. We have 60 years here, so that's pretty good. And we used normals. So as I've mentioned before, we just used like this long-term, we made an average long-term seasonal cycle and just ran the model with that. This is just to look sort of at the changes in the seasonality. We're not getting any variability or extreme events there, right? So that's a limitation. Also keep in mind, these integrated hydrological models, they have the groundwater component. The groundwater component is very slow to react. So you need to spin up your model. So from the historical state, which is already sort of in the ballpark, right? It still takes about at least 10 years to spin up to an equilibrium state for a climate change scenario. So you basically have to discard the first 10 years, at least. And then we just looked at what happened after that, right? But we do retain the seasonalities, and that's a very interesting aspect too. So this is the experimental setup we are going for. If you can computationally afford it, you can totally run transient simulations as well. You can run a continuous simulation from 1950 to 2100 if you have the computational resources. But remember to run multiple ensemble members over that. Okay, so let's look at the results. And so this is just stream flow. And on the right-hand side, so basically at the main outlet of the watershed, the gray is just the observed stream flow long-term average. The blue line is the historical simulated stream flow. So using the historical period WRF simulation, so regional climate historical period, and driving the hydrological model with that. That's so what we're showing with the blue lines. And the left-hand side is the G configuration, and the right-hand side is the T configuration. The T one is the one that has the very large precipitation bias in summer. So that's on the right-hand side. The top row is without bias correction, and the bottom row is with bias correction. So without bias correction, it's pretty evident that both of them are too wet, right? The T configuration, you might have expected it to be even wetter, but there's a compensating error in that the precipitation bias is compensated by a relatively large PT bias as well, because it has too strong solar radiation, essentially too little cloud cover, basically. The bottom row is with bias correction. So especially the left-hand side looks actually pretty good. The model is not perfect, but it looks pretty similar when we drive it just with observed climate. This is a natural state of the watershed, so there are no tile drains, for example, or no control structures. So we get more runoff sort of in winter, and the spring side is a bit smaller because we're not draining as fast as the tile drains would. The T configuration doesn't look quite as good, but it's still okay. So this bias correction seems to be sufficient. Now, if we are going to mid-century, there's a bit of an increase in winter precipitation. And so you see there's an increase in winter flow. There's also an increase in melt in winter. So that's why the flow in winter generally increases. But what you can also already see in WRF T is there's a decrease in flow in summer, right? And at end of century, this is pretty massive. So the red line now is end century. And if you compare the red line to the blue line in both of these cases, essentially the behavior between bias corrected and uncorrected, that's relatively similar qualitatively speaking. But the response between the different two configurations, WRF G and WRF T, is very different, right? So WRF T has significant drying, whereas WRF G is actually getting a bit wetter, especially sort of in late summer and fall. And so now you may wonder, so why is this the case? And I'll get to that. I just want to point out one more thing. There's one difference between bias correction and no bias correction, and this is the behavior in spring. And this is something where it's just an example where bias correction can actually affect your climate change response in some way. So be cognizant of that. And you have to make a judgment call, and you have to understand the physical reasons why this happens. So in this case, the decrease in runoff in spring is actually because the system dries out a lot over winter and fall in this end century scenario. And so a lot of the runoff in spring actually then a lot of it already melts in winter because it's warmer, and then it just recharges the groundwater rather than forming runoff. Whereas in the scenario without bias correction, the system is still so wet because of the precipitation bias that you're actually not getting this recharge response, and it actually does all form runoff. So you don't get the drying of or the drawdown of the groundwater because of the precipitation bias. And so, yeah, this is just an example of where you have to understand the processes and make a sort of a judgment of what you think is more realistic. And in this case, it's very difficult. Now here is the precipitation change that we are observing in the WRF G and the WRF T simulation, right? And so again, in the top is summer and the bottom is winter. And this is essentially the reason why we see the drying response in WRF T and the wetter response in WRF G, right? This is entirely driven by the climate projections. So drying in summer in WRF T, and this is because it has a different convection scheme, basically. Like the way that convective precipitation is represented is different. Whereas WRF G simulates an increase in convective precipitation. And this is just model uncertainty, and this is something you may encounter. And then the result of the study is essentially just inconclusive, and this is a possible result that you need to be open to. Because of model uncertainty in the Great Lakes region, we don't really understand very well what the climate change impacts are going to be. One thing maybe that's a bit more reassuring is in winter they're both projecting an increase in precipitation, and that's what most models do. But summer precipitation is more uncertain, right? And also note, these are 60-year averages, right? So this is not natural variability. We can be pretty certain that this is a model thing. This is because of the different ways that precipitation is represented in these two different simulation ensembles. And you will probably find something similar when you do your analysis, right? So be prepared for that. Okay. So just because we can, we'll have a little bit of fun looking at the subsurface response, right? So HydroGeoSphere is a fully integrated model, so you can look at the groundwater table. And as you might have expected, essentially, so on the right-hand side is WRF G, and on the left-hand side is WRF T, and on the left-hand side is WRF G. Essentially, the groundwater table response follows the general drying or wetting response that you see from the climate model or in the precipitation as well, right? So this is not really surprising, but what is interesting though is you can see a lot of regionally very varied responses. So there are some points where you see a large change in the groundwater table, so up to like in excess of 2 meters, right? Drop in or increase in groundwater table, whereas in other regions you see very little change, especially in stream beds. So as you get closer to the lakes, there's almost no change, right? And so this is actually pretty interesting because it's modulated by topography, right? And to drill a bit more into this, so this is sort of a cross section across the Grand River. So in the middle, this dip is the Grand River. And that's also why the water table is above the surface, right? That's the surface water. And then in these parts that have a strong relief where you have a higher topography, the water table is pretty deep. And this is the water table for the historical period. So WRF G and T after bias correction are pretty much the same, right? So after bias correction. But there are regions, especially in depressions, where the water table is almost at the surface, right? And so if you march this into the future, at the end of the century, you actually see a clear separation, right? And this change really follows whether or not the general hydrology becomes wetter or drier. But regions that have strong topography and deep groundwater table see a much larger change, whereas in depressions where the water table is almost at the surface, there's essentially no change in the groundwater table, right? So this is pretty interesting. So this is really strong modulation of climate change impacts by topography, which is something you really only get out of an integrated hydrological model. And you wouldn't get this from, let's say, a land surface model that's in a climate model also, or a rainfall runoff model, right? So to summarize this, there is a lot of uncertainty in climate projection. Most of this uncertainty is actually usually, and most studies find that, from the climate models. And this is why you need to use a large ensemble of climate models. And ideally also different models or at least different configurations, right? Do your data analysis so you understand the biases. This is important to interpret the results. Keep in mind that the impacts can differ seasonally. So here we saw it drying in the summer, but in winter much less so, right? And if you were to look at soil moisture, which we could, you would actually see this. You would see really significant change in soil moisture in summer, but much smaller changes in winter. Monthly normals can be useful, especially for model spin-up. But in arid regions, you have to be very careful with that. Here on the right-hand side is a checklist that you can go through for your own climate change impact analysis, and it's kind of summarizes what we've talked about. So are there any problematic lateral boundary conditions? Are you using temperature index models? If you do, you should probably get rid of them and replace with a physics-based method. Understand the dominant drivers, and if these are captured in your climate projections and also in your hydrological model, so like Great Lakes, topography. In Alberta, you're in the rain shadow of the Rocky Mountains. Is that captured? A lot of GCMs really smooth out the mountains, right? What do you need to do for spin up? Do you want to run a continuous simulation or a time slice approach? For a time slice approach, spin up is really critical. How are you controlling natural variability? So this goes back to what we talked about at the beginning. Monthly normals, over a long period, control natural variability very well. But depending on what your purpose or goal is, if you're interested in variability or if you're in a very arid region, this monthly normal approach may not work for you. So you may have to come up with something else. So this is essentially all I have to go over. We can discuss this now. You can ask questions. The floor is open. To start us off, I'll just answer the question about CMIP 5 versus CMIP 6. So CMIP 5 was from the 5th assessment report, the climate model that was based on. CMIP 6 is just the next iteration of the models. There are a lot more modeling centers now that have contributed, so the ensemble is larger for CMIP 6. The scenarios are somewhat different. The worst case scenario, the 8.5, is actually even worse. They added the new SSP 3-7 scenario, which is probably more likely. So basically, the worst case scenario from CMIP 5 was actually very unlikely. You would have to have an unprecedented level of economic growth and absolutely no mitigation to reach that. So it's pretty unrealistic. So the SSP 3-7 is probably more realistic. The models themselves changed as well. The resolution didn't really. Most models still run the same resolution they did in CMIP 5. So when you're looking at figures, you will not really notice the change. What changed mostly is the model physics. So the biogeochemistry got a lot more complex. The land surface models got a lot more complex. So some of them now added additional parameterizations for permafrost, for example. They did a lot of updates to carbon cycle models, dynamic vegetation models. A lot of them have now dynamic vegetation models. The ocean models often did increase in resolution. One major area of change is the cloud physics and the reflectivity of clouds, especially when it comes to the ice phase, so ice clouds. And this has actually led to, in some models, and the Canadian model is one of those, to significantly higher climate sensitivity. So these models show significantly more warming. And this is a major change between CMIP 5 and CMIP 6. So the overall average of the ensemble of the predicted climate change or warming is still similar, but the spread has become much larger because there are some models, including the Canadian model, which predict upwards of 5 degrees of warming. And this is new. So some models have become much more sensitive because of changes in the physics. I'm hesitant to say improvements of the physics, because in many cases it is newer physics, more sophisticated physics, but also physics that we don't understand as well, and it's not as well calibrated, and that may be the reason. So there's a bit of a debate in the community at the moment whether these more sensitive models are actually realistic or not. And you have to follow the literature, I think, on that. Okay. So Braden highlighted a question here by Luis Carlos.
Hi, Andre. I actually answered that question, but we do have a good question from Derek. If you scroll up in the chat, you'll see that. And then we've got another question here from Paul Martin.
Okay. Okay, yeah, so I mentioned the PDO alongside ENSO. Any comments on recent numerical studies? I'm not up to date on the literature on that, so maybe no. Is there anything specific you had in mind? Okay, so it goes a bit further. Okay, that cannot reproduce these oscillations without including external forcing from volcanoes. So this is interesting. I'm not aware of this. Volcanoes are strong perturbations of the climate system. Now, there are a lot of models, or most models, I should say, that do have these kind of oscillations without volcanoes. So they do seem to be internal to the system. They are probably triggered or sort of paced by external events to an extent. I don't know to which extent. So it's possible that there's an impact of volcanoes, certainly, because volcanoes do have a fairly strong impact on the climate system. And I could go to a slide at the beginning to actually show this. Derek, you could, yeah.
Yeah, I could explain a little bit. I mean,
yeah.
so it's, I think Enzo's understood as a couple.
Volcanoes.
Yeah. I think volcanoes was just an example. Like it might be, you know, some kind of aerosol or like, you know, non-consistent upwelling event or something. But if you had, say, like Enzo is well understood as like a natural internal mode because it's like from the atmosphere ocean coupling. If you some of the, like, I think some of the, you know, higher level researchers who do like numerical simulations are kind of have some of these internal oscillations kind of in their crosshairs because they don't get captured really well from looking at the governing equations and trying to fit them in with some type of internal oscillation framework, because there shouldn't be any. So I just was wondering if you were up to date on that or had any thoughts.
No, not really. Yeah.
That. Okay, sorry, theoretical stuff, but yeah.
Andre, we have another question from. We have a question from Paul Martin here, who asks if you can give us an idea of the time required to complete the Grand River model example, and comments about the budget. And just as you answer this, we might want to discuss maybe the time spent for different aspects of the project, from model construction to the climate data analysis portion.
Yeah. Okay. So this project stretched over a long time. So the climate simulations for that were done mostly in 2014-15. The project concluded in 2018. The papers were published 2019. So the hydrological modeling was done primarily in 2017. Each of those simulations would take maybe a few days. But in the end, we did a large set of simulations, a lot of different scenarios. So we looked at the 3 different time periods, but also each ensemble member individually, as well as the ensemble average. We did some transient simulations as well. We did with and without bias correction. We did a bunch of different sensitivity tests. So all in all, we did over 100 simulations, right, for that project. So in terms of compute time, it's actually over 100 days for the hydrological simulation. These were run on a workstation, though. So it's something that can actually be done sort of in-house, if you will. The climate projections themselves, they were run on a supercomputer at U of T. They took several months to complete, but each of those was run with 128 cores. So it's a lot of compute. And these were partially actually done by myself and partially by a postdoc at U of T. I did a lot of the data analysis on this, and I probably spent just a year or even more in the postdoc as well on data analysis just for the climate simulations. And then the analysis of the hydrological simulations probably also another year until we really understood what was going on there. And there's also a lot more, so I could talk about recharge and base flow and a lot of other things. But it's a fairly lengthy process, yeah. There's a hand up from Ed, I think. Maybe you just want to unmute yourself.
Yeah. Just to add to that, Andre, you had mentioned the Canada One Water project and its goals. You might, or I could indicate that all the data sets that go into HGS are basically prepared through that project for anywhere in Canada, also giving one the option to telescope into, let's say, a smaller region. So building these models could be facilitated through the C1 project, C1W project?
That's right. Yeah, yeah. So the Canada One Water project will essentially assemble data sets that facilitate the building of hydrological models at a large scale across Canada, right? Plus, we're doing the climate modeling. So it has both of these aspects, and these data sets will all be publicly available. And you could download them. So we haven't uploaded them yet to any repositories, but this will really facilitate that. The data sets themselves will be at higher resolution than we will run the large basin scale models, and most of them will be high enough resolution that they will be suitable to just carve out a little area of that and run a higher resolution model, something like the Grand River model or even higher resolution. So a lot of the input data sets will actually be something like 300-meter resolution, right? Like the DMs, even higher resolution. So this will really facilitate curving out small models and zooming in, but also building larger models and having them based on a consistent database, right? So that you can really make a modeling chain where you can solve this boundary condition problem with that, right? So we'll be running large basin scale models for the Great Lakes Basin, for example, or the Nelson Basin or the Mackenzie Basin, right? And at some point we'll publish these modeling results, and there will be, for example, groundwater table depth, like pressure heads available for climate scenarios from these large-scale models. And then the same climate scenarios will be available also for other people to do modeling with. And so you can use a climate scenario plus the predicted head from a large-scale model to do a small-scale analysis. So that's sort of the idea behind that. And we can, of course, help you with that.
And a follow-up question on the topic of these climate data sets. Paul Martin asks, what's our projection on when those data sets will be available?
That's a good question. And so we do have already historical simulations available. Future projections will be available probably in a year from now. Whether or not they'll be released in a year, it's maybe a different question because we'll have to look at them and do some quality assurance. And then there will also be a process afterwards, probably another year where we do bias correction. And so I would say between 1 and 2 years. If there's specific need for something now, we do also have the data sets, of course, from the Grand River study, and we do have CFCM5 data that's bias corrected that could be used almost immediately. But the simulations we're currently doing with CMIP 6 forcing, so like really the latest state of the art, that will be available in 1 or 2 years. And this is probably true for most of the regional modeling groups all over the world. Mm-hmm.
Okay, well, I don't see any other questions. So on behalf of everyone, over 40, almost 50 attendees here, thank you very much, Andre. It was very informative and lots to think about.
Yeah, thank you for your attention, and I hope you learned something. And
so I guess
don't hesitate to ask questions directly afterwards.
Exactly. Feel free to reach out to the team here at Aquanty anytime. You can reach us by emailing info@aquanty.com. You can also reach out to Andre or I personally. We'd be happy to answer any questions as well.